Before we finish looking at proof by contradiction, I want to look at a particular type of theorem that we almost always use proof by contradiction on, and that is proving that a given real number is irrational. So we're first going to define rational numbers and irrational numbers so we know what we're talking about. We're going to talk about why directly proving a number is irrational can be really difficult, if not impossible. And then we're going to prove that square root of 2 is an irrational number. Alright, so a rational number, as we've seen before, that is a type of real number that has the form a over b, where a and b are both integers, and of course b is not equal to 0, because of course you can't have 0 in your denominator. So, as an example, 4/7 is a rational number because, well, it really well fits the definition of rational number. The numerator 4 and the denominator 7 are both integers. 7 is not equal to 0. Negative 2/9 is a rational number. Well, it doesn't look like a rational number now because it has that negative sign. It's negative a rational number. But if we rewrite it as negative 2 divided by 9, then we can see that, oh yeah, negative 2 and 9 are both integers. 9 is not equal to 0, and so negative 2/9 is a rational number. And even integers like 5, those are rational as well, because even though it doesn't look like a fraction now, we can rewrite 5 equal to 5 divided by 1. That's a fraction. The 5 and the 1 are both integers, and 1 is not equal to 0. So lots of numbers. Most of the numbers in your real life that you come across are rational numbers. But of course, the real numbers don't just contain the rational numbers. They also contain some other ones, and those are the ones we call irrational number. So an irrational number is a real number that is not a rational number. It is completely defined by not being a rational number. All right. Now, as you can imagine, it's pretty straightforward to prove directly that a real number x, say, is rational. Maybe not easy, necessarily, depending on the problem, but straightforward. You look for two integers, a and b, such that the denominator b is not equal to 0, and x equals a over b. So when you take a over b, you happen to get x. If you get any two numbers that do that, you're in great shape. You've proven that it's a rational number. For irrational numbers, it's going to be a little bit difficult, right? Because we don't have any affirmative definition of what irrational numbers are. We only really have a definition based on what they're not. I mean, they are real numbers, so that tells us something, but they're not rational. That's basically all we know besides that. So that makes it really difficult to prove it directly, which means we almost always need to prove it by contradiction. And we also use another little tool that I'm not going to prove this fact. This fact is something that's borne out from your experience with fractions, and it can be proven. So if you're really worried about it, I'm glad to talk to you about it and how you would prove it. But we have an additional assumption that we're going to make when we're dealing with fractions, and that is every fraction of integers can be written in lowest terms. And of course, what lowest terms means is that we've canceled out everything that we can to make the numerator and denominator as small as possible. So that means we've canceled out all the common factors in the numerator and denominator, so that the only common factors between the numerator and denominator, well, we can't get rid of all of them. 1 and negative 1 are the only ones. Okay? So now we're going to use these tools to prove that the square root of 2 is irrational. Now, of course, we're going to prove this by contradiction, which means that we are going to assume that our theorem is false, that square root of 2 actually is rational. And then we're going to prove, well, that's the thing with proof by contradiction. We don't know exactly what we're going to prove. We just know we're going to prove something that's false. So basically what we're going to do is we're just going to wander around until we happen to run into something. Oh, hey, here's a false thing that we've just proven, and then the theorem is over. So we're going to start with what we're assuming, that square root of 2 is rational, and then we're going to wander around, see if we can figure out what the contradiction is. So rational means that the square root of 2 is equal to a over b, where a over b is integers, b is not equal to 0, blah, blah, blah. All that good stuff, right? And also, for the sake of this proof, we're going to assume that our fraction a over b is in lowest terms. In other words, we've canceled out everything we can so that the only common factors between a and b are 1 or negative 1. All right, so let's go ahead and wander. So we're going to start with square root of 2 equals a over b. Okay, so I'm not too fond of the square root, so it might be a good idea to square both sides so we can get rid of that square root. We end up with 2 equals a squared over b squared. You know what? Fractions aren't so great. Why don't we multiply both sides by b squared to get rid of the denominator, just to make it look nicer? I mean, I don't know what I'm looking for. We'll just keep on going. So when we multiply both sides by b squared, the left-hand side becomes 2 times b squared. The right-hand side, the b squareds cancel, and you just get a squared. Now, looking at that left-hand side, the 2 times b squared reminds me of even numbers, right? And b is an integer, so b squared is an integer. So that means that 2b squared is going to be an even number, right? So if 2b squared is an even number, that's equal to a squared. That tells us a squared is an even number. All right, well, that's something. And actually, we proved something way back when we were doing biconditional statements. We proved that a squared is an even number if and only if a is an even number, which means that if a squared is even, that means a is even. So that's a theorem we actually proved in class. We don't have to prove that again for this proof. We can just cite it so that the reader knows we're not cheating, right? We're not trying to pull a fast one. All right, so a is even. And so, well, I guess we can use the definition of an even number, right? A is equal to 2k, where k is in z. We're still wandering, right? We don't know what we're doing. But actually, we can take that a equals 2k, substitute that into that equation a couple lines up, that 2b squared equals a squared, right? So we get 2b squared equals 2k quantity squared, and that becomes 4k squared. And actually, if we divide both sides of the left-hand side and the way right-hand side by 2, we end up with b squared equals 2k squared. And actually, that looks really familiar because, again, k squared is an integer, 2k squared is an even number, and that says that b squared is an even number. And, we can use the same reasoning as with a squared being an even number. That means b is an even number. And so let's see what that tells us. So that tells us that a and b are both even numbers. But wait a minute. If they're both even numbers, that means they share a common factor of 2, right? And that tells us that a over b is not in lowest terms, but we were assuming it was in lowest terms. That's a contradiction. All right. So we wandered into a contradiction just totally, well, it wasn't by accident, right? But you can imagine doing this sort of reasoning and kind of just wandering into this contradiction. So that worked out nicely for us. So we start off by proving, or assuming that square root of 2 is rational number, and then proving, and assuming that a over b is in lowest terms, and then proving that a over b is not in lowest terms, and that's contradictory. Excellent. All right, so let's see what the formal version of that proof is going to be. The real number square root of 2 is irrational. That's our theorem. Let's go ahead and prove it. Now, of course, the first thing we're going to do for our reader is we're going to be nice to them and assume that we're going to, and tell them that we're proving this by contradiction. And that means we're going to assume that square root of 2 is a rational number and prove a false statement, or if you prefer, we're going to prove a contradiction. They both mean the same thing. So, since we are assuming square root of 2 is a rational number, we can write square root of 2 equals a over b, where a and b are integers and b is not equal to 0. We're doing the exact same reasoning that we did on the previous slide, right? And then the next thing we did was square both sides, right? By our previous remark, okay, I forgot about that. We can also assume that the fraction a over b is in lowest terms, which means that a and b do not share any common factors other than 1 or negative 1. All right, so that was our assumption that we were making. We can make it. Again, we didn't prove it, but if you want me to prove it, I will. All right, so now we're going to square both sides. We're going to take the equation square root of 2 equals a over b, square both sides. We get 2 equals a squared over b squared, right? Then we multiply both sides of the equation by b squared to get rid of the denominator. We get 2b squared equals a squared. Now, remember, we were making the even number arguments. So, since b is an integer and the integers are closed under multiplication, we know b squared is an integer. That means that 2b squared is an even number, and since that's equal to a squared, that means a squared is also an even number. Now, we remind the reader that we proved previously in class that if the square of an integer is even, then the integer itself is even. Since a squared is even, that implies that a is even. Now, the next thing you remember, we use the definition of even number. Now we can use the definition of even numbers, right, to conclude that a is equal to 2k, where k is an integer. That means that a squared is equal to 4k squared if we square both sides. And since a squared is equal to 2b squared, we get 4k squared is equal to 2b squared. Now we can't divide both sides of the equation by 2 to get 2k squared is equal to b squared. And then we remind our reader that k squared is an integer, and so that means 2k squared is even, which means that b squared is even. Since b squared is even, we know b is even. We've already gone through this reasoning before, so we don't have to cite our theorem again. And now we've sort of been running our reader around in circles, so it's good to sort of center ourselves and remind our reader, hey, here's what we've proven. We proved that a is even, and then we also proved that b is even. And that means a and b both have a common factor of 2. And now we hit them with the contradiction. But this contradicts the fact that a over b is in lowest terms, since it has a and b have a common factor of 2. This is a contradiction. We're telling our reader we have a contradiction, so they know that the end of the proof is here. And so we can conclude that square root of 2 is irrational. All right, so now you can try out some of these arguments on the in-class activities. The name of the PDF file that's included with this video is Irrational Numbers.